Group 20's project is called TURF, which stands for Turf Upkeep and Robotic Field Care. The team consists of 3 members: 2 computer engineers, Ari and Sam, and 1 electrical engineer, Andrew, which is myself. Lawn care is something most homeowners deal with regularly, but it comes at a cost of their money or their time. Mowing your lawn can easily take hours every week, especially in sunny climates like Florida. For busy families, that's time that could be spent working, studying, or relaxing. On the other hand, hiring a lawn care service removes that time burden, but it becomes a recurring expense that adds up quickly over months and years. While autonomous lawn mowers exist as an alternative, current models are very expensive to purchase, and many require boundary wire installations that increase setup costs and complexity. Our project aims to provide a more affordable and practical solution.
Our solution is a robot mower that uses ultra-wideband localization, a cost-effective alternative to LiDAR systems that remains more precise than satellite-based localization. Ultra-wideband localization works by measuring the round-trip time of a Bluetooth packet between the robot and an anchor. The anchor remains at a fixed location, giving us a point of reference. Once we know how far away the robot is from 3 anchors, we can draw circles of the known distances to find out where they intersect. The point of intersection is our current location.
Our base goal is to develop an affordable autonomous lawnmower capable of navigating a pre-programmed coverage area reliably and efficiently. Safety is a top priority, so we're implementing obstacle detection and an emergency stop system to prevent damage or injury. We are also developing a companion mobile app that allows users to control the mower, monitor status, and configure settings. Our advanced goals focus on convenience and scalability. We aim to implement automatic docking and charging so the mower can return to its station when the battery is low. We also plan to modularize the design, allowing interchangeable tools in the future, such as different blades or attachments. Finally, our stretch goals push the system towards further autonomy. We want to enable smart scheduling and weather aware operation, allowing the mower to pause and resume automatically during rain. Additionally, we hope to integrate computer vision for advanced object detection, enabling dynamic avoidance of pets, people, and unexpected obstacles. Our objectives are measurable technical deliverables that demonstrate system functionality and safety. At the base level, we are implementing localization using ultra-wideband technology, which allows the mower to determine its position within a defined area. We are also developing a full control system for propulsion, steering, and the mowing motor. A key performance objective is to demonstrate at least 10 minutes of fully untethered autonomous mowing within a defined test plot. For safety, we are integrating an ultrasonic rangefinder to stop the mower before obstacles. Finally, we are designing and fabricating a durable, weather resistant housing to protect the electronics and cutting mechanism. For advanced objectives, we plan to build and demonstrate an automatic docking and charging station. We also aim to implement a programmable mowing schedule, allowing the mower to operate autonomously on a set weekly routine. For stretch objectives, we plan to integrate computer vision using OpenCV to detect foreign objects in the mower's path for safety, and implement weather detection for rainy days. This slide shows how we translated marketing requirements into measurable engineering specifications. At a high level, the mower must provide full lawn coverage, operate efficiently, remain safe, be easy to recharge, and stay affordable. But we'll focus on a few key technical specifications. First, for navigation accuracy, we are targeting position estimation error of less than 20 centimeters relative to field anchors using ultra-wideband localization. This level of precision ensures straight mowing rows and consistent coverage. Second, for safety, the system must detect obstacles at least 1 meter away and come to a stop within half a meter. This provides a clear safety buffer for people, pets, and equipment. Finally, for usability, we are implementing an automated docking station with a recharge time of 10 hours or less. This reduces user involvement and supports true autonomous operation. These highlighted specifications are critical because they directly impact accuracy, safety, and real-world usability.
Our system is built around 3 tightly integrated components. The mobile app, built in React Native, gives the user a live visualization of the mode area and communicates with the robot via a REST API connected through a Wi-Fi hotspot. On the hardware side, we're running C++ firmware on ESP32 microcontroller, which handles all the motor control and safety logic. For positioning, we use a dual-layer approach, GPS-anchored trilateration as our primary method, with dead reckoning for error correction. And in order to validate the software without waiting on the robot build to be completed, I tested the software stack using a Node.js simulation environment on Windows. This slide breaks down the internal architecture of our firmware, which is structured into 3 distinct layers. The first layer is our hardware abstraction layer. It handles pulse width modulation for the drive motors and analog to digital conversion for battery monitoring. The second layer is a localization engine, where we combine dead reckoning with trilateration from our 3 anchor points to continuously calculate the robot's X and Y coordinates. The third layer keeps our robo state and field config decoupled from each other, meaning that if Wi-Fi connection is temporarily lost, the robot retains its positional data and can continue its mowing pattern without needing external input. Here we have the architecture of our mobile app, the core of which is our Mower API service class, which manages all HTTP requests and handles timeouts to keep the app responsive even on a weak Wi-Fi signal. For state management, the app pulls the mower every 2 seconds and updates a central mower status object. We also built in a safety layer that continuously scans incoming telemetry. If the firmware reports a coordinate mismatch, the app immediately pushes an alert to the user. This represents a bridge between low-level firmware and clean user experience, translating the raw coordinate data into a visual progress bar and an easy emergency stop button. This is the state diagram, reflecting how we designed RoboMo as a finite state machine to keep its behavior predictable in a real-world environment. The mower starts in an idle state until it receives a field configuration from the app, which would be uploaded by the user, at which point it transitions to a ready state. A start command then engages the blade and drive motors, entering the mowing state. There's 2 automated transitions from here, where if the battery drops below 10%, the mower stops the blade and enters a return state, navigating back to the origin where the charging dock is located. The other autonomous path is emergency stop, which is a global override that can be triggered from any state, immediately cutting power and transitioning to a stop state for the user to come and manually inspect, allowing safety to take precedence over any current state of the mower. Communication between the app and the mower starts with a connection handshake, where the mobile app sends a GET request to the ESP32, which responds with the current telemetry, including battery level and coordinates of the mower. Once the user taps resume mowing, the app gets a post command, triggering the firmware to engage the blade mower and begin the autonomous mowing pattern. From there, the system enters a control loop where the localization engine fuses the position data and sends updated commands to the motor controller every 50 milliseconds. On the safety side, emergency stop is handled asynchronously. It bypasses the navigation loop to immediately invoke stop motor and stop blade. We also have a check that pushes an automated alert to the app if localization error exceeds 0.5 meters, ensuring that the mower does not drift off its intended path. To validate the system, we ran tests across multiple key areas. For network latency, API connection consistently came in under 2 seconds. Emergency stop latency was under 50 milliseconds, fast enough to confirm immediate motor shutdown in the event of an emergency. For navigation precision, we fused trilateration and dead reckoning, keeping position accuracy within half a meter, which is what we need to reliably stay within the defined field boundaries, and make sure that no places are missed when mowing. The deployment side, we confirmed a successful APK installation on an Android device and validated a data transfer between the device and a hotspot connection on our simulated ESP32 environment. For the mobile app, I considered using both React Native and Flutter. Although Flutter has a slight edge in raw UI rendering performance, I chose to use React Native with ExpoGo for a few key reasons. A single codebase for both iOS and Android development, a streamlined cloud pipeline through EAS build, and my existing familiarity with the framework. Trade-offs are dependency on using ExpoGo and a slightly larger APK install sizes compared to a native build, but given the rapid development cycle and the complexity of syncing real-time robotics, I decided it was the right call. For firmware development, we evaluated 3 environments. ESP-IDF is the native framework for the ESP32 and supports advanced real-time operating system features, but the setup complexity was a significant barrier given the timeline that we had to work with. MicroPython was appealing for rapid prototyping, but its large memory overhead and slow execution speeds made it incompatible with the high-frequency control loops that our navigation system requires. We ultimately chose C++ with the Arduino framework, giving us direct GPIO access, a small memory footprint, and fast execution, while still being practical to develop in. Also let us integrate external libraries like Arduino JSON for mobile communication. For a system that requires precise motor control and real-time sensor fusion, C++ was an easy choice.
Here you can see our hardware design. We have 4 subsystems: a power subsystem that handles voltage regulation, a receiver and kinematics subsystem which contains the ultra-wideband module and microcontroller, the motor subsystem which is responsible for movement, and a transmission tag subsystem which constitutes our fixed anchors. Transmission tags are physically disconnected from the other subsystems which remain on the robot. Communication takes place over Bluetooth. We had 2 main choices for the type of logic processor we would implement: single-board computers, SBCs, or microcontrollers. Single-board computers, such as the Raspberry Pi family of devices, have very high processing capabilities compared to microcontrollers, but are unsuitable for our needs for several reasons. Single-board computers require more complex circuitry for integration, cost significantly more, and consume much more power. Additionally, the general-purpose operating systems that typically run in SBCs would not meet the deterministic performance necessary for our system to ensure safe and precise operation. While slower, microcontrollers would suit our low-power deterministic requirements. There were 3 microcontrollers considered: the ATmega328, which is used in older versions of the Arduino Uno, and 2 ESP32 variations. The ATmega328 was quickly discarded as an option due to its very low speed and lack of free RTOS support. Of the 2 ESP32 options, the main difference was just the amount of RAM and flash storage available. We chose to go with the ESP32 Rover since it had significantly more memory and storage than the ESP32 Room, and cost marginally more. The additional memory would better suit the multitasking needs of our system. Our localization system needed to be affordable. We determined 3 methods that would facilitate this goal. Dead reckoning is a method that would use feedback from the motor Hall effect sensors to estimate current position based on past actions and movement. It would require the minimum cost to implement, but is very imprecise and accumulates drift over time. GNSS or GPS was an immediate consideration, but it is not precise enough to neatly mow a lawn and self-navigate. GNSS accuracy can be enhanced with correction data, but that would incur complexity beyond the scope of our project. Ultra-wideband localization was ultimately determined to be the only remaining choice. It is affordable and precise. One disadvantage remains. At least 3 anchors must be in range of the robot at all times for accurate localization, which poses concerns with scaling to very large areas. There are only 2 commercially available ultra-wideband ICs, the DW1000 and the DW3000. The DW3000 is an improved version of the DW1000, offering greater resistance to interference at almost the same cost. However, we chose to go with the DW1000 since it offers a more mature ecosystem with better community libraries. We chose to use the same PCB design for the main board on the robot and for the anchors. It reduces time spent on development and testing, and marginally increases our cost compared to developing a separate anchor design with a cheaper microcontroller. Here are the schematics for our main board. The ESP32 is in the center, the DW1000 module is in the lower right, and in the top right is a USB UART bridge that was selected based on the advice of Dr. Weeks. The LMR60440 was originally selected to step down our battery voltage to 3.3 volts, but we were advised against it due to a high switching frequency. Dr. Weeks recommend using the LM2576, which has a slightly lower efficiency but much lower switching frequency, making it more stable and less sensitive to PCB layout. Here is our schematic for the voltage regulator. The LM2576 requires minimal support circuitry, with just a couple of capacitors, an inductor, and a protection diode present in our design. The layout of our regulator board matches the reference in the datasheet as closely as possible.
This slide shows our motor selection trade-offs for the propulsion system. We evaluated 4 options: brush DC with Hall sensors, brushless DC, and stepper motors. A basic brush DC motor is simple and low cost, but it has no speed feedback and wears over time, which makes it imprecise for autonomous navigation. Stepper motors provide precise positioning, but they are inefficient and draw higher current, which makes them unsuitable for a battery-powered mobile platform like ours. Brushless DC motors are efficient and long-lasting, but they require more complex drivers and are excessive for our low-speed application at this stage. We ultimately selected a brush DC motor with Hall sensors. It allows closed-loop control using PWM with feedback, giving us better velocity and direction control while remaining cost-effective. This gives us the precision we need without significantly increasing system complexity or cost. This slide shows our motor driver comparison between the DRV8874 from Texas Instruments and the L6206 from ST Micro. The DRV8874 operates from 4.5 to 37 volts, which fits well within our 9 to 12 volt battery system. In contrast, the L6206 supports higher voltages up to 52 volts, which is unnecessary for our application. In terms of control, the DRV8874 supports PWM or phase enable control, making it very straightforward to interface with our microcontroller. The L6206 uses separate logic inputs, which adds unnecessary complexity. The DRV8874 also provides strong built-in protections, including undervoltage lockout, overcurrent protection, and thermal shutdown. Combined with its low drain source resistance, it offers higher efficiency as well. Because of its high integration level and efficiency, we selected the DRV8874 as a better fit for a 9 to 12 volt robotics platform like our autonomous mower. I'll briefly walk through our motor driver schematic design. We use the DRV8874 motor driver and the phase enable mode to control a brush DC motor using PWM from the ESP32. The VM input comes from our battery supply and is decoupled with capacitors. The current limit is set using the iProp I pin. I selected a 1.5k ohm resistor, and with a Vref of about 1.2 volts from the divider, this sets the current trip point to approximately 1.8 amps, which is safely below the motor's stall current. To improve electrical isolation between the ESP32 and the motor driver, I added 3 6N137 optocouplers on the control signals. Each optocoupler includes a resistor on the input side and a 10k ohm pull-up resistor on the output side. This protects the microcontroller from noise and voltage spikes generated by the motor. For our PCB design, we focused on placing our decoupling capacitors as close as possible to the VM and VCP pins. This helps reduce voltage ripple and switching noise during motor startup and braking. We also separated power and control routing using a solid ground plane, added thermal vias under the exposed pad of the DRV8874, and kept high current VM traces wide and short. The board passes ERC, DRC, and Dr. Weeks checks and is optimized for clean current flow and noise reduction. For hardware testing and performance evaluation, we're currently limited by the fact that our PCBs haven't arrived yet, so full system testing will happen over the next few weeks once we can assemble the final hardware. That said, we've already done preliminary proof of concept testing using development boards, mainly to verify that our localization approach is feasible and behaves the way we expect in a real environment. Once the PCBs come in, our main evaluation metric will be autonomy. The robot should be able to cover a defined 10 meter by 10 meter test area without any user control. We'll measure how consistently it covers the area, whether it maintains its planned path, and whether it can handle basic stopping behavior when it detects obstacles.
For our budget, we were aiming to keep the final prototype to under $500. We purchased 4 ESP32 microcontrollers for $24.52, 4 Anchor modules for $94.48. We spent $19.17 on the chassis. Our custom PCBs came in at $149.85, and Miscellaneous components and spare parts added another $186.82, bringing our subtotal after taxes and tariffs to $512.78, which is just barely over our goal. However, it is worth noting that this includes all of our spare parts, so the total prototype will actually come in just under the $500 goal. Here we have our distribution of labor. I handled the mobile app development on my own and collaborated with Arian on the microcontroller firmware. Arian took control of the hardware side, leading both the main board and regulator board development. Andrew was responsible for the motor driver board development himself. Overall, it was a good division of labor that let us work within our strengths while also having some overlap to collaborate with each other when needed. Here we have a physical rendering of our robot. There are three key design principles worth highlighting here. First, we went with a pre-made chassis rather than designing one from scratch. We did this to save development time and let us focus our efforts on the firmware and software, as well as the PCB design, which were the more complex challenges for this project. We used tracked wheels instead of traditional round wheels to have more traction in off-road surfaces, which is very critical for lawn mowing application as the ground conditions can vary a lot. It also includes charging contacts at the base, which is what enables our autonomous self-docking behavior.
Here is our project timeline and where we are today. We finalized the overall system architecture and selected all major components, including the MCU, sensors, motor drivers, and power system. After that, we validated the design through breadboard prototyping, focusing on motor control, MCU integration, and localization modules. Currently, our PCBs and parts have been ordered and are awaiting delivery. Over the next few weeks, we'll assemble and test the boards, complete software development, and move into full hardware firmware integration. Beyond that, the focus will be debugging, performance tuning, and system enhancements. Thank you for listening.